All right. Hello, everyone. All right. Hope everyone is doing good this Monday morning. Let me set up this. Just a moment. All right. Unit 11. All right. So in the previous class, I have introduced these two new functions as new operations for math. Okay, remember? Let me make a page here, which allows me to do this. All right. There you are. Math operations. Math operations are the one that we know before this class is addition, subtraction, multiplication, and division. These operations are function itself, right? It's inverse. So let me put here operations or functions. The inverse function or the inverse operation of this one are for addition is subtraction. For subtraction is addition, multiplication is division, and for division is multiplication. All right. So this one are the inverse. The two new operations are the exponential function. Okay. Let me put it like this: a raised to the x, right? And the logarithm function, the one that we are going to work today. The inverse function of the exponential function is the logarithmic function. Let me put it here because it's not perfect like this, but the thing that I want you to get is that the inverse operation of the exponential function is the logarithmic function and vice versa. The inverse operation of the logarithmic function is the exponential function, right? Today, we are going to work with the logarithmic function. But in order to understand the logarithmic function, since the notation or if you will, the notation of this operation is different than the previous one because now we are introducing the word log or log to represent or to express the logarithmic function. All right. All right. So going back to unit number 10, we know that the parent function, the exponential parent function, is the one that is here. F of x equal a being a positive whole constant value that is not equal to 1. A raised to the power of x. Okay, and with that we can get the following points. So we have when x is equal -1, we have 1 over a. When x is equal 0, we have 1. And when x is equal 1, f of x is just a. We have here an horizontal asymptote, and the asymptote is y equals 0. So the domain of the exponential function are the real numbers, but the range is just from 0 to positive. So with this, we have the graph of the exponential function, something like this, and here it will be -1, 1 over a. Here it will be 0, 1, and here is 1 or 1, comma a. Okay, this one, when x is equal to 0, we call this one the initial value. Right? So that's a review from previous class. Why are we seeing this? Well, because now we are going to compare this with its inverse function, which is the logarithmic function. Right? I should move this down. Better. Okay, so let's have g of x equals log base, let's use a as the base, of x. We read this as g of x equal log base a of x. Okay, a little weird, but this is how we do it. Okay. All right. So you will see that the domain of the logarithmic function is or the domain for the logarithmic function here need to be greater than 0. Okay. So all positive numbers. So for the logarithmic function, here we are going to have 3 key points as well. And this time the key points I'm going to use this number here to get the key points, right? Because we're saying that the logarithmic function is the inverse operation of the exponential function. So the inverse operation, what basically do is to flip the y with the x coordinate. Okay, so here I'm going to start with the y coordinates, -1, 0, and +1. And I have taken this number, -1, 0, and 1, from here. Right? So that means, since logarithmic function log base a of x is the inverse operation of a raised to the power of x, so we have that the x coordinates are going to be 1 over a, 1, and a. Okay, so those are the key points. We make this small. So exponential function has a horizontal asymptote. The inverse operation, the logarithmic function, now turns that horizontal asymptote into a vertical asymptote, and here at x equals 0. Domain is, so the range of the exponential function, so the domain will be from 0 to positive infinity. Remember, it is the inverse operation, so the range of the function is going to be the domain of the inverse operation. And the range, then it will be all real numbers. All right, so let me try if I can, let me just try something here. Let me copy and paste this. I wonder if I can do this. So let's rotate this. Nope, it will get ugly. So let's draw the graph of the logarithmic function. First thing, we flip the horizontal asymptote into a vertical asymptote, right? And then we have this. Something like this. This is the shape of the logarithmic function. So we have 1 over a, negative 1 here. We have 1, 0, and we have a and 1. Okay. So the draw is not perfect, it's just a representation. So that what we are just seeing here is the shape of the parent function. Okay, exponential on the left, logarithmic function on the right. Okay. Any question? Last but not least, to solve equations with the exponential function or the exponential operation, on the previous class we used this property. So if we have an equation, both sides are exponential function and the base is the same, we conclude that the exponent need to be equals. Okay, and we use this property to solve equations. Okay, so now let's say that we want to solve or the property that we are going to use to solve equation with logarithmic function is going to be the following. So the property says, we read the property as this. Log base a of x is equal b. The meaning of this is that the exponent that we need to raise a in order to get x is b. Okay, let me give you an example to give you a better explanation of this. So let's say log base 2 of 8. Go to your calculator and tell me what is the value of this. Brenna, you said 2. Check that again. Let's go to our calculator. All right. It's 3. I believe not all the calculator have the ability to put 2 as the base. So let's do another one, and I'm going to solve this one because Bernard already solved it. He put give us the answer on the chat. But let's use another one with one that you can do with your calculator. So log base 100. Okay. So the first one is log base 2 of 8 is 3. Okay. Now let's see log without base. So you need to remember what is the meaning of this. Log of 100. What will be the answer here? So we go to our calculator. Let me see how my calculator handled this. I believe it's 100 first and then log. Okay. This is equal to 2. All right. So let's see how we can use the property here to understand these values. Well, if I take 2 raised to the power of 3, what is the value of that? 3 raised to the power of 3. Two raised to the power of 3, I believe. I think I said 3 to the power of 3. 2 raised to the power of 3. What is the value? Tell me that on the chat. It's 8. Right? So you can see that the base here, the base for the logarithmic function is 2, and the base for the exponential function is 2 as well. Now, the thing that changed or flipped here is the argument. The argument of the logarithmic function is what is in those parentheses. So it's 8, and 3 is the result. So 3 is going to be the exponent of the base 2 that give us the argument 8, or a value of 8, right? For this one, when we are not seeing the base here, that means that the base is 10. So 10 squared is equal to 100. So the bases are both 10. The result of the logarithmic function is going to be the input in the exponential function, and the input in the logarithmic function is going to be the output of the exponential function, right? And this is what we are going to use to solve equations with logarithmic functions. Another important logarithm is natural log. Natural log means that the base is e. Okay, and remember, e is just a letter that we use to represent a value, like pi or something like that, right? That's another one that's important. In the calculator, you usually will have ln or log, log base 10 or natural log. One more concept before we start with the exercise is that we have multiple ways to write values, to write the value. For example, we use numbers, 0, 1, 2. So each of these symbols represent a value of 0, a value of 1, a value of 2. These are not the only values. We could write 1.5, that's a decimal value. Or a decimal number. So there is how we write a value, right? We also can write values like this one, square root of 2. So that's a value. We are using a mathematical operation, but that's just a value. Pi, we are using here a symbol, but it is representing a value, right? And we can use logarithms to also write values, like this one, natural log of 2. Okay, this here is representing a value, and we will treat this notation as just a number. Okay, so when you have natural log of 2, for example, in an equation, you are going to treat natural log of 2 as just a number. Okay. You will get something like this. So natural log of 2 is just a number. And if we want to solve here for x, what we need to do is just to divide both sides by natural log of 2. That way, we've canceled this factor, and x is going to be 1 over natural log of 2. Okay, but see that we could use the operations on natural log of 2. Here we could divide it on both sides of the equation just to get rid of it on the left side of natural log of 2. Okay, so remember this, because since we are going to start working with equations with logarithms, you need to remember that ln or log base something of a number is just a representation of a value. That's it. Okay, questions? All right. So first exercise is where we need to determine the domain of this logarithmic function. Always the argument is what is in between those parentheses. The argument of any logarithmic function need to be greater than 0. So in order to get the domain, what we're going to take is the argument, and we are going to say this need to be greater than 0. Be careful with this inequality, because here what we have is a quadratic equation on the left side. And if you go and try to solve this equation like this, at this point you will need to use square root of on both sides of the equation. What is the problem of using a square root here? What happened? What is the problem now? If I do this, is there a problem? If you finish, if you do this, is this correct? Yeah, we cancel the power of 2. But what was that's correct? Yes, Ari. Here we have two cases. The plus minus brings two cases. So if you write this, it won't be correct. The solution here is not explicit. So we need to break this into two parts, into two cases, and we need to say we take the positive case, so x need to be greater than 3. That's okay, nothing happened there. But with the minus, like you said, Ari, now the inequality flips. Okay, and now this is going to be the solution. We could do another thing to understand better this conclusion. We have been working with polynomials on the past units, so we could use those properties. So we have here the factorization of the quadratic equation x squared minus 9, or quadratic polynomial, So we can identify the zeros. So the zeros are 3 and -3. Then we could go and put those zeros on the number line. We know that the multiplicity of the polynomial of the factor here are odd, so the behavior of the graph at those zeros is that it will cross. If we go and then we test for 0, so x equals 0, we are going to get 0 minus 3, and then 0 plus 3 here. The important thing here is to know the sign. Is it positive or negative? After we solve this, so the 0 just get cancelled, so we got -3 times +3, and we know that this is going to be negative. So this part here between -3 and 3 is going to be negative. Since we have an odd multiplicity for both zeros, this part here is going to be positive, and this part here is going to be positive. And we were looking for greater than 0. So we can translate our finding here on the right side to a interval from -infinity to -3, union 3 to +infinity. And that is the domain of this logarithmic function. This conclusion here is the same as what we have here. If we read this, I can rearrange this, putting the negative first and then the positive case after. I'm going just to rearrange what we have here. So we know that x needs to be less than 3 and x need to be greater than 3. Okay. This part here, we can translate this into an interval from -infinity to -3. And this part here, we can translate this into an interval from 3 to +infinity. And then we just have to do the union. Okay? And we got the same answer or the same conclusion. The thing here is that you could do this first, what I did here first. Okay? But you need to understand what is happening here. Okay? What is happening here, if you want to justify what is happening here, you can use the properties of the polynomial, and then you will justify why we have two cases. Okay? But at the end, it's the same process. It will get you the same conclusion. For the test, you just need to do just one of these things. If you like to continue working with the properties of the polynomial, well, you do the right side. If you just want to work algebraically here, you can do the left side, but be careful with this. Okay? The only thing that you need to do is to be careful in your conclusion, okay? And use well the mathematical properties. Any question? Right? Okay. So this one, we need to draw the graph of log base 4 of x. Four is the base, x is the argument. And here you are going to go back to the previous, to the first test, where we introduce the parent function and the transformations. Okay. First thing that you are going to do here is to identify the parent function. Parent function. Let me use just y, not f of x. the parent function here is log base 4 of x. That's it. Key points. So key points for the parent function. Okay. How are we going to get the key points here? Well, you can remember that we can use 1 over the base. That we can use 1 and then just the base. Okay, but where do these numbers come from? They come from the inverse operation, 4 raised to the power of x. Okay, so let me use y prime here as the inverse operation of the parent function. If we are going to work with this one, this is an exponential function. So to get the key point of the exponential function, we use x as -1, 0, and +1. And then we get the values of 1 over 4, 1, and 4, right? So if you go and see this number here, the output of the exponential function are basically, are the same for the input in this case here, because log base 4 of x is the inverse operation of the exponential function that we have here on the right. Okay, so just in case you forget what value go on the input for the logarithmic function, check the inverse operation. Okay, all right. So y here is -1, 0, and +1. Okay. So these are the key points of this the logarithmic function base 4 of x. This function has a vertical asymptote at x equals 0. And that's all what we need for the parent function. Now let's identify the transformation. The transformation here is just 1. What we have here is just vertical reflection, so that means that all the y values are going to be multiplied by -1. So this function, the key points or the new points here are going to be just the same, with the difference that we're going to multiply the y values by -1, and that is the point that you are going to use to put them on the coordinate plane. So here we go here. We have a vertical asymptote. You will click here to set the vertical asymptote, and then you will plot the point using this tool here. The domain, remember you take the argument greater than 0. Here you need to translate this into an interval notation, to get the to write your answer. And the range, remember that their logarithmic function do not have restriction on the range, so the range is going to be all of real numbers. Okay. Questions? So here the exercise where you are going to use the property that we discussed before about the logarithmic functions. So we need to solve this equation. We need to solve for x. X is part of the argument of this logarithmic function. So there is a problem. So how are we going to get x out of the logarithmic function? Okay. So the first thing is that we want to have the one logarithmic function in one side of the equation. So these three here need to go on the right side. So we divide both sides by 3, and then we got natural log x natural log x plus 5 equals 2. Right? Then how are we going to eliminate this logarithmic function? So let's use the property. The property here says, first thing is that we need to identify the base. Let me change ln for log base e. This is the same, they are equivalent. The only thing I'm doing is just making explicit the value or the base of this logarithmic function. Okay, but we are talking about the same. Why do I want to see the base? Well, because in order to solve this exercise, I need to rewrite this equation as an exponential function. E, using the base here, e raised to the power of 2, so what I have on the right side equals x plus 5. Okay, see that what I'm using is the inverse operation, the inverse function. Okay, the base raised to the power of 2 equals the argument. And now this is just a linear equation. Okay, remember that it's just a number. So what we have here is an equal equation. E is not a variable, E is a value. This is a linear equation, and what we need to do is just to subtract both sides by 5 to get x equal e squared minus 5. Questions? Okay. This exercise says do not round any intermediate computations, and our final answer need to be round to the nearest hundredth. So we go to our calculator. E squared minus 2 minus 5, sorry, e squared minus 5, and nearest hundredth, so that means 2 decimal places, 2.39. And that's the answer. Okay, and that's how we solve equations with logarithmic functions. Let's do another one. Okay, so the problem again is that we have x confined in the argument of this logarithmic function. I need to isolate the logarithmic function first, so I want to have one logarithmic function on the left side of this equation. To do that, I will add both sides by 7, and then I have log base 3 x plus 7 equals 3, right? Now let's turn this logarithmic expression into an exponential expression. Okay, let's use the inverse operation. So 3 is the base, and this 3 now goes here as an exponent, and all this is going to be equal to x plus 7. Now we are working with a linear equation because 3 raised to the power of 3 is 27. And what we need to do here is just to subtract both sides by 7. So x is equal 20. Okay. The important part here is to isolate the logarithmic function in one side of the equation, so have one logarithmic function in one side of the equation, and then using the exponential operation or the inverse operation, we can turn the logarithmic equation into an exponential equation that usually is going to be a linear equation. Okay, linear, or it's going to be a polynomial equation, and then we can solve it. Questions? Okay, so let's try this one. This one will get pretty obvious once we translate this logarithmic function or this logarithmic equation into exponential function or exponential equation. Okay, write on the chat how you will write how will you use the inverse operation to find the value of x. Okay. What will be the next step in order to find the value for x? Okay, don't do that on the chat. Okay, remember to use the property. The property that we are going to use is we take the base of the logarithmic function, we take the output of the logarithmic function, and we use it as the input of the exponential function, and then the argument goes out. Okay, this is what it is important here. And I have here Brian says 81 raised to the power of 1/2 equals x. That's correct. What is, when we have an exponent of 1/2, what is the meaning of that? Do we know how to solve that? When we have an exponent, a rational exponent, we can turn that into a radical. So any number raised to the power of 1/2 means the square root of that number. And the square root of that number, in this case 81, is 9. So x is equal to 9. Okay? So it makes sense because 9 square is equal to 81. Okay, so a square root of 81 is 9. Okay, so that is the value for x. Let me see what else we have here before doing that one. Okay, let's do this one. Okay, take 3 minutes to try to solve this one. Let me know in the chat when you have an answer. Okay, we're gonna have negative 10. Okay, anyone else? All right. All right. So upon inspection here, we have one logarithmic function in one side of the equation. That's what we want. So that means that the next step will be doing turning this into an exponential equation. We take the base, which is 5, and we take 2. That's correct, Brian. 2, which is the output of this logarithmic function. We use it as the exponent of the base. And the argument goes on the right side here. Here, what we need just is to solve for x, because now we have a linear equation. Solving for x, and you got negative 10. Okay. Okay. In this exercise, we go backward. So now the variable is in the exponent. So you might want to try to find a common base between both sides of the equations to then use the property that if both sides are exponential functions and they are the same in an equation, and we have the same base, then we conclude that the exponent need to be equal. That is not the case here. Now we are dealing with an exponential equation where there is no common base. Okay, so what are we going to do here? We are going to explore this type of exercise more on the next unit. Okay, but to give you a first kind of an introduction of what we are going to do when we do not have a common base, is that now we are going to use the logarithmic function to eliminate the exponential function and brings down the exponent. Okay, so here what we know is that the base of this exponential function is e. I want to eliminate that exponential function or that exponential operation because my variable is in its exponent. Okay, I want to bring down my variable y. I know that there is a logarithmic. What we are going to do is just to use logarithmic function on both sides of the equation, and the base of that logarithmic function is going to be the same base of the exponential function or exponential operation that I want to eliminate. The one that I want to eliminate is e raised to the power of 7y. Doing so, and here happen two things. The first thing that happened is that the exponent now turns into a factor of this logarithmic function. Right? And next, log base e, or natural log of e, it get cancelled because this result into 1, because the exponent that we need to apply to e in order to get e is just 1. So we erase this, we cancel that, and 7y equals log base e of 7. Okay. We divide both sides by 7, and y is equal log. I'm going to use ln. Okay, natural log is the same as log base e. ln of 7 over 7, and this is the value. Remember that ln of 7 is just a value. Okay, the only thing is that we are using a different method to write that value. So that is the value of y. I think the other thing that we need to do is to round the final answer to the nearest hundredth. So what we need to do is to get our calculator out. 7 natural log divided by 7. Around 0.2. Okay, this exercise is important, okay, as we are going to continue working on this type of exercise on the next unit, because on the next unit we are going to be solving equations, exponential equations, where there is no common base, and hence we need to use the logarithmic functions in order to eliminate those exponential functions, and doing so we bring down the exponent, and the exponent here are going to contain the variable that we are going to solve for. Okay, so this is just a brief introduction, or a brief introduction of what we are going to do on the next units. We are going to be working with equations with multiple logarithmic functions, and we are going to be working with equations with exponential equations with no common base. Okay, so we are going to start playing with the properties of the logarithmic functions and the property of the exponential functions. Okay, so I hope this is a good introduction for what we are going to do next. The property that I use here are two. We are going to discuss those properties on the coming units, where we are going to be dealing with this type of exercise. Any question before we finish our class? All right then. So I have a great rest of the day. Okay. So I'm going to be grading your test this week. I don't know. I believe maybe before Friday we have your grade. If you have any questions, you know where to reach out. And happy Monday to everyone. I will see you on Wednesday.